Section: Introduction. In this section, we delve into the observation that deep learning advancements, from the inception of AlexNet to the development of transformers, have shown a distinct preference for solving classification problems effectively with large neural networks. Even in situations where a regression-based approach might seem more intuitive, converting the problem into a classification task often leads to better outcomes. This conversion involves changing real-valued targets into categorical labels and focusing on minimizing categorical cross-entropy instead of mean-squared error. Various reasons have been proposed to explain why this approach tends to be more effective, including the stability of gradients, the ability to form better representations, an implicit bias towards more useful solutions, and a more effective way to handle imbalanced data. These reasons suggest that the benefits of this approach could extend beyond just supervised regression tasks. Contrary to the trend in supervised learning, value-based reinforcement learning (RL) methods have predominantly relied on regression. For instance, deep RL techniques like deep Q learning and actor-critic models use a regression loss, specifically mean-squared error, to train a value function based on continuous scalar targets. Despite the success of these methods, scaling them up to larger networks, such as high-capacity transformers, has been challenging. This difficulty in scaling has been attributed to various factors, but we propose a question. What if we could achieve the same level of scalability seen in supervised learning by simply reimagining the regression problem as a classification problem? To explore this idea, we conducted a comprehensive study to assess the effectiveness of different methods for creating classification labels to train a value function using a categorical cross-entropy loss. Our findings indicate that using cross-entropy for training value functions significantly enhances the performance, robustness, and scalability of deep RL methods compared to traditional regression-based techniques. The most effective method we identified leads to a consistent 30% improvement in performance when scaling parameters with mixture of experts in single-task RL on Atari. A 1.8 to 2.1 times increase in performance in multitask setups on Atari. A 40% improvement in the language agent task of Wordle. A 70% improvement in playing chess without search. And a 67% improvement in large-scale robotic manipulation with transformers. This consistent improvement across various domains, network architectures, and algorithms underscores the substantial benefits of treating regression as classification in deep RL, highlighting its potential as a key component in scaling up value-based RL. With strong empirical evidence supporting the use of cross-entropy as a direct replacement for the mean-squared error (MSE) regression loss in deep RL, we also sought to understand the source of these empirical gains. Through detailed diagnostic experiments, we found that the categorical cross-entropy loss addresses several issues inherent to deep RL, such as robustness to noisy targets and enabling the network to more effectively utilize its capacity to fit non-stationary targets. These insights not only help explain the strong empirical advantages of using categorical cross-entropy in deep RL but also offer guidance for developing more effective learning algorithms in the field. Moving on to the preliminaries and background, we approach regression from a probabilistic perspective. Given an input, we aim to model the target as a conditional distribution with a certain mean and fixed variance, using a predictor function parameterized by a vector. The traditional approach involves using the mean-squared error (MSE) objective to find the optimal predictor. However, an alternative approach involves learning a distribution over the target value and then recovering the prediction as a statistic of this distribution. To achieve this, we frame the regression problem as learning a parameterized distribution that minimizes the KL divergence to the target distribution, which is essentially the cross-entropy objective. Our prediction is then recovered from this learned distribution. To make this problem tractable, we limit our learned distribution to a set of categorical distributions supported on a defined range with evenly spaced locations or classes. The final step involves defining a procedure to construct the target distribution and its projection onto the set of categorical distributions, which we discuss in more detail in the context of RL. In the realm of reinforcement learning, RL, we consider the problem where an agent interacts with an environment by taking actions in current states and receiving rewards before transitioning to the next state based on the environment's transition probabilities. The agent's goal is to learn a policy that maximizes the expected return, which is the cumulative discounted sum of rewards. Deep Q networks, DQN, propose learning an approximately optimal state action value function with a neural network, specifically minimizing the mean squared temporal difference, TD, error from sampled transitions. Most deep RL algorithms that learn value functions follow this basic approach, notably regressing to predictions obtained from a target value network. We also explore the offline RL setting, where agents are trained using a fixed dataset of environment interactions. One widely used offline RL method optimizes the TD error alongside a behavior regularization loss. Our work aims to replace the fundamental mean squared TD error objective with a classification-style cross-entropy loss for both value-based and actor-critic methods, in both offline and online domains. Section Summary. In this section, we explore the effectiveness of treating regression problems as classification in deep reinforcement learning, RL. By training value functions with categorical cross-entropy loss instead of mean squared error, we observe significant improvements in performance, robustness, and scalability across various tasks and architectures. This shift not only enhances empirical results but also addresses inherent issues in deep RL, offering a promising avenue for developing more effective learning algorithms in the field. Section: Value-based RL with classification. In this section, we explain our method of transforming the regression challenge found in TD learning into a classification problem. Instead of focusing on reducing the squared difference between the scalar Q value and its TD target, we aim to minimize the difference between categorical distributions that represent these values. To do this, we first need to establish a categorical representation for the action value function, Q, S, A. We decide to depict Q as the expected value of a categorical distribution, Z, which is defined by probabilities for each class or location, based on the outputs of a softmax function applied to logits. This setup allows us to use the cross-entropy loss for TD learning, provided that the target distribution is also a categorical one, supported on the same set of locations. To calculate the cross-entropy loss, we ensure that the target probabilities are defined in such a way that their sum across all locations approximates the TD target. We explore two methods for determining these target probabilities. The first method involves projecting the scalar TD target onto a categorical distribution supported by the locations. A simple but flawed approach is to discretize the scalar into one of several bins, which can introduce errors into the Q function. To address this, we consider a too-hot strategy that accurately represents a scalar target with a unique categorical distribution that assigns non-zero probabilities to two locations surrounding the target. This method, while more accurate, does not fully take advantage of the ordinal nature of discrete regression, where classes have a natural order and are not independent. To leverage this ordinal structure, we introduce the concept of histogram losses, which distribute probability mass across multiple neighboring bins, similar to label smoothing in classification. This is achieved by transforming a noisy version of the target value into a categorical distribution where probability mass can cover several bins near the target. Specifically, we define a random variable with a probability density and cumulative distribution function, whose expectation is the TD target. We project this distribution onto a histogram with bins centered at each location by integrating over a specified interval to obtain the probabilities. We suggest using a Gaussian distribution for this purpose, where the variance is a tunable hyperparameter that influences the amount of label smoothing. Tuning the standard deviation, in addition to the bin width and distribution range, is crucial. We recommend adjusting the ratio of the standard deviation to the bin width to control how the probability mass is distributed across neighboring locations. In our experiments, we set this ratio to ensure that the mass is spread across approximately 6 locations, providing a balance between accuracy and smoothness. Section Summary. In this section, we describe our approach to transforming the regression problem in TD learning into a classification problem by minimizing the distance between categorical distributions representing Q values and their TD targets. We introduce methods like the too hot approach and histogram losses to project scalar targets onto categorical distributions, aiming to improve the accuracy of the Q function by leveraging the ordinal structure of discrete regression. These techniques provide non-lossy representations of scalar TD targets and distribute probability mass to neighboring bins, enhancing the performance of value-based reinforcement learning algorithms. Section: Modeling the categorical return distribution. In this section, we explore a different approach to understanding future financial returns by directly modeling their distribution with our categorical model, Z, similar to techniques used in distributional reinforcement learning, RL. Specifically, we look into C51, an early method in distributional RL, which models future returns by categorizing them and then minimizing the difference between the predicted distribution and the actual distribution of returns. This method contrasts with our previous strategies, such as too hot and HL Gauss, for creating target distributions for our cross-entropy objective. To model the categorical return distribution, we first define a stochastic distributional Bellman operator on Z, where the action at the next time step, A_t+1, is chosen by picking the action that maximizes the Q value of the next state and any possible action. This operator changes the positions of our categories, Z_I, requiring us to project these changes categorically. This projection spreads out probabilities to the immediate neighboring categories based on their position relative to the reward received at the next time step plus the discounted value of Z_I. To identify these neighboring categories, we use the floor and ceiling functions, which help us find the categories closest to a given value from below and above, respectively. For a detailed explanation of this projection method, we refer readers to the original documentation. Our experiments aim to test how well various target distributions, when combined with categorical cross-entropy loss, improve the performance and scalability of value-based deep RL across a range of tasks. These tasks include playing Atari 2600 games, language processing, chess, and robotic manipulation, covering both online and offline RL scenarios. For each task, we apply our cross-entropy losses alongside a proven value-based RL method. The full details of our experimental setup and the specific parameters used are available in the appendix. When focusing on single-task RL with Atari games, we compare the performance of HL Gauss, too hot, and C51 against a baseline trained with DQN using mean squared error for the temporal difference objective. We use the Atom optimizer for training, which helps minimize the performance gap between regression-based methods and distributional RL approaches. We evaluate our methods based on the interquartile mean, IQM, of normalized scores, with confidence intervals calculated using stratified bootstrap, across multiple games and seeds. Our results show that HL Gauss not only outperforms too hot and mean squared error losses but also does better than C51, indicating that the choice of loss function might be more critical than the specific modeling of the return distribution. In the context of offline RL, the strong performance of HL Gauss with online DQN prompts us to investigate its effectiveness with offline datasets. Training agents with different losses on a subset of the Atari DQN replay dataset using CQL, we find that HL Gauss and C51 consistently outperform mean squared error, with too hot showing more stability than mean squared error but not performing as well as the other classification methods. Notably, HL Gauss again surpasses C51, reinforcing the idea that cross-entropy losses are more stable and do not degrade over time as mean squared regression loss does. Lastly, we examine whether our classification methods can help scale value-based deep RL to larger networks, a strategy that has proven effective in supervised learning, especially for language modeling. Unlike in supervised learning, simply increasing the number of parameters in deep RL methods can sometimes lead to worse performance. Our findings suggest that using classification methods as an alternative to mean-squared error regression loss can enable better performance scaling for value networks in deep RL. Section Summary. In this section, we model the categorical return distribution by directly representing the distribution over future returns using a categorical model Z, inspired by distributional RL techniques like C51. By defining a stochastic distributional Bellman operator on Z, we can shift and scale locations Z_I to project probabilities proportionally to neighboring locations, improving performance in various RL tasks including Atari games and beyond. Our experiments show that using categorical cross-entropy loss with different target distributions like C51 and HL Gauss enhances scalability and performance in value-based deep RL, outperforming traditional regression-based losses. Section: Scaling with Mixture of Experts. In this section, we explore the concept of scaling with a technique known as Mixture of Experts, MO. Recently, it has been shown that while increasing the number of parameters in convolutional networks can negatively impact the performance of single-task reinforcement learning (RL) on Atari games, integrating MO modules into these networks can actually enhance performance. Following this approach, we substituted the second-to-last layer in the architecture used by Impala with a soft MO module and experimented with different numbers of experts, specifically 1, 2, 4, and 8. Each expert is essentially a duplicate of the original penultimate layer, which means the number of parameters in this layer increases by a factor that matches the number of experts. The only modification we made was to replace the mean-squared error (MSE) loss in soft MO DQN with the HL Gauss cross-entropy loss. We conducted our training on the same subset of 20 Atari games previously used in similar studies and reported our findings based on the aggregate results over 5 different seeds. Our findings, as illustrated in the referenced figure, indicate that the HL Gauss loss consistently enhances performance over the MSE loss by a constant factor, regardless of the number of experts involved. It's also worth noting that the combination of soft MO with MSE appears to alleviate some of the negative impacts of scaling observed with MSE alone. This improvement might be attributed to the use of a softmax function in the penultimate layer, which could offer benefits similar to those provided by a classification loss. However, as we will discuss later, these benefits cannot be fully explained by the addition of the softmax function alone. Moving on to training generalist policies with ResNets, we aim to scale value-based ResNets in both offline and online settings to develop a generalist video game playing policy for Atari. We trained a variety of Q networks of different sizes for multitask RL and evaluated performance based on network size. In the online multitask RL scenario, we trained a policy capable of playing different Atari game variants, each with unique dynamics and rewards. We focused on 2 games, Asteroids and Space Invaders, evaluating 63 and 29 variants, respectively. We utilized a distributed actor-critic method, Impala, and compared the standard MSE critic loss with the cross-entropy-based HL Gauss loss. Our experiments aimed to understand how these losses scale when transitioning from smaller Impala CNN networks to larger ResNets, up to RESNET 101. After training for 15 billion frames and repeating each experiment with 5 seeds, we found that HL Gauss consistently outperforms MSE in both environments. Notably, HL Gauss shows better scalability, especially evident in Asteroids, where it even slightly improves performance with larger networks beyond RESNET 18, while the performance with MSE significantly degrades. In the context of multi-game offline RL, we adapted a setup to use a non-distributional HL Gauss loss instead of the distributional C51 loss. We trained a single generalist policy to simultaneously play 40 different Atari games, learning from a near-optimal training dataset composed of replay buffers from online RL agents trained independently on each game. Our findings show that HL Gauss scales even better than the C51 results, achieving about a 45% improvement over the best prior multi-game result with RESNET 101. Furthermore, While MSE regression losses typically plateau when increasing model capacity beyond RESNET34, HL-Gauss leverages this capacity to improve performance, highlighting the effectiveness of classification-based cross-entropy losses. Lastly, we evaluated the applicability of the HL-Gauss cross-entropy loss beyond Atari by considering tasks that utilize high-capacity transformers, including playing Wordle, chess without inference time search, and robotic manipulation. For the language agent task of playing Wordle, a word-guessing game, we aimed to see if classification losses could enhance the performance of value-based RL approaches. We trained a GPT-like, decoder-only transformer model with 125 M parameters, representing the Q network, and found that HL-Gauss outperforms MSE across multiple coefficients controlling the strength of CQL regularization. This experiment underscores the potential of classification losses in improving the performance of value-based RL approaches in language agent benchmarks. Section Summary. In this section, we explore the impact of scaling with mixture of experts, MO, in convolutional networks for single-task RL on Atari games. By incorporating MO modules in the network architecture, we observe improved performance, especially when using the HL-Gauss cross-entropy loss instead of MSE. The experiments show that HL-Gauss consistently outperforms MSE, even mitigating negative scaling effects and scaling better with larger networks, showcasing the effectiveness of classification-based cross-entropy losses in enhancing RL performance. Section: Grandmaster-level chess without search. In this section, we delve into the innovative approach of achieving Grandmaster-level chess without relying on traditional search methods. We've discovered that transformers, known for their versatility in approximating algorithms, can significantly reduce the need for costly computations at inference time through a process called distillation. Specifically, we explore the advantages of utilizing HL-Gauss to transform scalar action values into classification targets, which aids in distilling a value function. By employing the setup used in previous studies, we assess the effectiveness of HL-Gauss in distilling the action value function of Stockfish 16, the most powerful chess engine that combines intricate heuristics and explicit search, into a causal transformer. Our distillation dataset is extensive, consisting of 10 million chess games annotated by the Stockfish engine, resulting in 15 billion data points. We trained 3 transformer models with different capacities, 9 million, 137 million, and 270 million parameters, using either HL-Gauss or one-hot classification targets. We decided to exclude mean squared error, MSE, from our comparison as one-hot targets have shown superior performance for this task. The effectiveness of each model was evaluated based on its ability to solve 10,000 chess puzzles from Lichess, with success measured by the accuracy of the generated action sequences compared to known solutions. Our findings reveal that while the one-hot target with the 270 million parameter transformer outperformed an AlphaZero baseline without search, HL-Gauss significantly narrowed the performance gap with the much stronger AlphaZero that utilized 400 Monte Carlo tree search (MCTS) simulations. Moving on to the realm of generalist robotic manipulation with offline data, we investigated whether cross-entropy losses could enhance performance in large-scale vision-based robotic manipulation control tasks. These tasks involve controlling a simulated 7-degree of freedom mobile manipulator to successfully grasp and lift 17 different kitchen objects amidst distractors, clutter, and randomized initial poses. We created a dataset of 500,000 episodes, both successful and failed, starting from a small set of 40,000 human teleoperated demonstrations. By replaying expert demonstrations with added action noise, we mimicked failed autonomously collected rollouts observed during deployment or evaluations of a behavioral cloning policy trained on the human demonstration data. We trained a Q transformer model with 60 million parameters, following a previously established recipe but replacing the MSE regression loss with the HL-Gauss classification loss. Our results showed that HL-Gauss achieved a 67% higher peak performance over the regression baseline, demonstrating much greater sample efficiency and addressing a key limitation of the prior regression-based approach. We also sought to understand why classification losses significantly improve the performance and scalability of value-based deep reinforcement learning, RL. Through controlled experiments, we explored how the categorical cross-entropy loss could tackle challenges specific to value-based RL, such as representation learning, stability, and robustness. Additionally, we conducted ablation studies to pinpoint the reasons behind HL Gauss's superiority over other categorical targets. In our ablation study, we identified two main differences between classification losses and traditional regression losses used in value-based RL: the parameterization of the value network's output as a categorical distribution instead of a scalar, and the strategies for converting scalar targets into a categorical target. We found that parameterizing the Q network to output logits, which are then converted to probabilities of a categorical distribution using the softmax operator, leads to bounded Q values and output gradients. This could potentially enhance the stability of RL training. However, when we trained Q functions with this parameterization but used MSE instead of cross-entropy loss, we did not observe any performance gains. This underscores the significant role of the cross-entropy loss in achieving performance improvements. Furthermore, our results indicate that HL Gauss outperforms 2-hot, despite both methods utilizing a cross-entropy loss. We hypothesize that HL Gauss's advantages may stem from two factors: its ability to reduce overfitting by distributing probability mass to neighboring locations, and its capacity to generalize across a specific range of target values by exploiting the ordinal structure in the regression problem. Our experiments in the online RL setting across a subset of 13 Atari games supported these hypotheses. We varied the number of categorical bins and the ratio of deviation to bin width, finding that HL Gauss consistently outperformed 2-hot. This suggests that HL Gauss's effectiveness is not solely due to mitigating overfitting, as is commonly believed with label smoothing, but also due to its ability to leverage the ordinal nature of the regression problem. Section Summary. In this section, we explore the benefits of using HL Gauss to convert scalar action values into classification targets for distilling a value function. We trained transformer models on a dataset of 10 million annotated chess games to distill the action value function of Stockfish 16, achieving competitive performance compared to AlphaZero. Additionally, we demonstrate that classification losses, particularly HL Gauss, significantly enhance the performance and scalability of value-based deep RL by addressing challenges specific to value-based RL such as representation learning, stability, and robustness. Section: What challenges does classification address in value-based RL? In this section, we delve into the challenges that classification addresses in the realm of value-based reinforcement learning, RL. We've observed that the improvements in performance from cross-entropy losses are due to both the adoption of a categorical representation of values and the use of distributed targets. Now, we aim to understand the specific challenges in value-based RL that cross-entropy losses help to mitigate, at least to some extent. First, we explore whether classification is more resilient to noisy targets compared to regression. Classification tends to be less susceptible to overfitting when faced with noisy targets because it focuses on the categorical relationship between inputs and targets rather than their precise numerical relationship. We examine if classification can better handle noise introduced by the inherent stochasticity in RL. For instance, when dealing with noisy rewards, we test the robustness of classification to stochasticity in rewards by adding random noise to each dataset reward in an offline RL setup. We adjust the scale of this noise and compare the performance of a cross-entropy-based method with that of mean squared error, MSE, loss. Our findings show that the performance of the cross-entropy-based method declines more gracefully as the noise scale increases. Additionally, we consider the stochasticity in dynamics by conducting experiments in an environment with sticky actions, which introduces non-deterministic dynamics. When we disable sticky actions to compare different losses under deterministic conditions, the cross-entropy-based method and MSE perform similarly, though both outperform a distributional approach. This suggests that one of the benefits of cross-entropy losses is their reduced tendency to overfit to noisy targets, a common issue in RL environments with stochastic dynamics or rewards. Next, we question whether classification leads to more expressive representations. It's well known that relying solely on mean-squared regression error does not yield useful representations in value-based RL, often resulting in representations that struggle to fit target values observed during further training. Predicting a categorical distribution rather than a scalar target can lead to better representations, capable of modeling value functions of various policies encountered throughout the learning process. We investigate this by examining whether representations learned from value networks trained online still retain the necessary information to relearn a policy from scratch. Our experiments show that cross-entropy losses indeed result in better performance, indicating that they foster more expressive representations that support the value improvement path of a policy trained from scratch. Lastly, we consider whether classification performs better amidst non-stationarity, a characteristic inherent to value-based RL due to the constantly evolving policy and value function. We first look at a synthetic regression task to simulate non-stationarity and then control for non-stationarity in an RL context by running offline SARSA. Our findings suggest that classification losses maintain higher flexibility under non-stationary targets compared to regression. However, in the offline SARSA setting, the advantages of the cross-entropy-based method over MSE loss are less pronounced, adding evidence that some benefits of classification stem from its ability to handle non-stationarity in value-based RL. To summarize, our exploration reveals that the use of cross-entropy loss is crucial for achieving good performance in value-based RL. While these methods do not tackle any specific challenge head-on, they enable value-based RL methods to better deal with non-stationarity, foster highly expressive representations, and provide robustness against noisy target values. Section Summary. In this section, we explore the challenges that classification addresses in value-based RL. We find that classification is more robust to noisy targets compared to regression, especially in scenarios with stochastic dynamics or rewards. Additionally, classification leads to more expressive representations and performs better amidst non-stationarity, making it a superior choice in value-based RL problems. Section: Related work. In this section, we delve into the existing literature that intersects with our study. Previous research in areas such as tabular regression and computer vision has shown a trend of substituting regression tasks with classification to enhance performance. A notable contribution in this realm introduced the H.L. Gauss cross-entropy loss for regression, demonstrating its effectiveness in small-scale supervised regression tasks outside of reinforcement learning, RL. Our research builds upon these foundational works by showcasing, for the first time, how a classification objective, particularly when trained with cross-entropy loss like H.L. Gauss, can be effectively scaled for value-based RL across diverse domains. These domains include video games like Atari, robotic manipulation tasks, chess, and the game Wordle. Several leading-edge methods in RL have employed the too-hot cross-entropy loss, often without thorough analysis. This approach has been used either as a makeshift solution, citing advantages for handling sparse rewards, or based on informal knowledge. However, our experiments indicate that too-hot underperforms compared to other cross-entropy losses and mean-squared error, MSE. We attribute this to too-hot's inability to adequately spread probability across neighboring classes, a feature that both C51 and H.L. Gauss manage effectively, as we explore in a detailed empirical investigation. Our work also aligns with research on categorical distributional RL. A significant analysis in this field has been the examination of categorical one-step distributional RL, which closely resembles the too-hot algorithm. This similarity had not been acknowledged before. Furthermore, the pioneering work on the C51 algorithm, although not primarily focused on framing RL as classification, hints that the choice of loss function might play a pivotal role in the success of the algorithm, possibly more so than modeling the return distribution itself. Other studies have recognized the importance of categorical distributional RL losses for scaling offline value-based RL. However, these studies have not pinpointed which aspects of this approach are essential for achieving positive scaling trends. It's important to note that our findings do not conflict with recent theoretical advancements arguing that distributional RL offers statistical advantages over standard RL, independent of the use of a cross-entropy objective or categorical representation. Previous research has extensively analyzed the representations learned through TD learning, focusing primarily on MSE losses. Very little attention has been given to understanding the representations learned through cross-entropy-based losses in RL. Our linear probing experiments aim to address this gap, revealing that value networks trained with cross-entropy losses learn better representations than those trained with regression. This discovery is particularly significant as prior studies did not identify any representational advantages of HL-Gauss over MSE in supervised regression, suggesting that cross-entropy could offer substantial benefits specifically for TD-based learning methods.